about today. First, I want to make 3 comments about yesterday, so that hopefully some confusions or unclear things will be clarified. So first, I remember that somebody was asking about the Susy transformations and how many supersymmetries there are in 11 dimensions. So I decided that it's good to start here so that I can also remind the notation. So in this lecture, the metric I'll denote with capital G, because soon I'll introduce a small g that will be the metric in 10 dimensions. So the 11-dimensional metric is capital G. And these are the rules, the supersymmetry transformation rules of 11-dimensional supergravity. So again, gamma are just the gamma matrices, psi is the vector spinor, and the spinor index, as usual, is here suppressed. This is the 3 form, and it transforms into the gravitino. And the gravitino transforms into a combination. So, of course, the metric is involved because of the various index contractions, but also there is the 3 form. And, well, F with 4 indices, this is, as a form, is just D of A3, where A3 is this 3 form. So we see actually that this so-called flux term has some involved combination where the indices of F are contracted with gamma matrices. So the action that I wrote last time, actually I only wrote the bosonic part, but for completeness, one should write all other terms, including fermions and couplings. And then the whole action is invariant under those transformations. And the parameter of the transformations is just one single spinor, epsilon. So that's the Susy parameter in 11 dimensions. So that's why we say that there is n equals 1 supersymmetry. That means that there is one parameter in 11 dimensions. But this is a spinor in 11 dimensions. So it has 2 to the 5th components, which means 32 supercharges. So there is one supersymmetry, the minimal amount, but there are 32 supercharges. And if we compare that to 4 dimensions, in 4 dimensions, what would it mean to have n equals 1? It would mean one spinor, but the one spinor would have 4 components, so 4 supercharges. So n equals 1 in 11 dimensions is not the same as n equals 1 in 4 dimensions. In fact, n equals 1 in 11 dimensions, or 32 supercharges, corresponds in 4 dimensions to n equals 8. And that's what one obtains by, say, dimensionally reducing 11-dimensional supergravity to 4 dimensions on a torus. One obtains exactly n equals 8 supergravity. So, and one can build, well, the Susy representation with all the states that we counted yesterday, just with the action of the Susy charges, like usual. I'm not going to do this here, but let me mention that there is a nice reference if somebody wants to, read in more detail. It's even a textbook, so it should be written well. So if you want to learn more about how to build the representations in 11 dimensions and how to see that this is a super multiplet, you can look in the book by Weinberg. This is quantum fields, I believe. Yeah, quantum field theory. And this is volume 3. So actually, the whole volume 3 is about supersymmetric field theories, with or without gravity. So for anybody who wants to learn more, this is a good place to look. And in particular, these representations are described in section 32.2. So you can read there about the Susy algebra and how you can build representations in any dimension. So I'm not going to go into more detail about this. Let me just mention another thing that yesterday was maybe unclear or puzzling. And that's related to the notion of spin. So that was the first point I wanted to clarify from yesterday. Another point was about spin. So somebody was asking, what is the spin of those fields? And I said the metric has spin 2, the gravitino spin 3 halves, and the 3 forms spin 1. And at the time, I didn't say more. I guess I was kind of surprised by the question, but later on I realized that maybe it's a very good question because somehow it seems clear how it can be confusing. For example, why the 3-index antisymmetric tensor would use with spin 1. But again, if you read this section, it will become very clear how those things work. So, but let me just mention this. How would we define spin in higher dimensions? So the key difference is in 4 dimensions, we remember that the little group was just in 4D is just SO2. So it's easy to label the representations, and that's the label spin. Now, I mean, one label is enough. In D dimensions, there are more labels needed. So one needs to specify how exactly we define spin. And the definition is, so definition, spin of a representation of the little group, which is SOD minus 2, is the maximal value the maximal absolute value I hope I'm not going too fast through this, but I want to get to the lecture that was supposed to be today, so don't want to waste too much time with those qualifications. Okay, the maximum absolute value of the eigenvalues of any Lorentz generator in the representation. In the representation in question. For example, the representation that was the tree form, the rank 3 anti-symmetric tensor. If one looks in more detail in this section, one can see that some generators have a maximal absolute value 0, others have 1. So we just compare the different ones and pick the largest one, the maximal one, and that determines that this has spin 1. And similarly, one can see for the other fields how the counting goes. So hopefully that makes this more clear. And maybe I should have said something like that yesterday, but somehow it did not occur to me. And finally, also, let me try to clarify the issue about the degrees of freedom of the gravitino. And I thank to the guy here who pointed that out. I wasn't careful about that either, but one of your colleagues apparently knows a lot and was paying attention. So let's see. So the third point I want to clarify before beginning the actual lecture is about the gravitino degrees of freedom Actually, I should say that what I said yesterday, I just briefly took a look in a book by Becker, and Schwartz that is called String Theory and M Theory. But apparently that book was sloppy and not quite right. So I'll try to explain something more. But first, let me just say that the irreducible representation, or the spinor that is irreducible representation is indeed, in fact, a spinor which is of this form, vector spinor. Dot just means contraction of the vector indices. So this is gamma n, psi n. So this is irreducible representation that gives the spin 3/2. So when we counted the degrees of freedom, remember we had 9 times 16, and we wanted to subtract 16 more, which corresponded to a spin 1/2. And this is indeed, without subtracting this term, we would have a reducible representation that would contain also this part. So this is like subtracting the trace when we were handling the metric. and we had a symmetric but traceless matrix that was giving the degrees of freedom for the graviton. Similarly, this can be called trace part here in this context. It's like a trace. So this is the analog of taking a traceless combination. Actually, I can say more about the gravitino, but maybe if there is time at the end, it might be useful to do an honest counting of degrees of freedom like we did for the metric. Again, yesterday I hadn't thought about that yet, but hopefully today, if there is more time, I'll go through that. Just looking at the various constraints that we have and seeing how this counting really comes about without trying to use any shortcut. So, any other questions about yesterday? And if not, I'll finally move to the new topic. I hope that was at least a little bit helpful. Yeah? No, that was the difference, right? We were trying to subtract from the number of components the various gauge invariances so that we have the actual degrees of freedom. So this, which has to be 128, is the actual degrees of freedom. But again, here I have not shown that in detail. So that's what I'm saying. If there is time at the end, I'll show how to start indeed from just the total number of components and remove all gauge invariances and constraints in order to obtain the actual degrees of freedom. So yesterday I was more detailed about the metric and the vector field, but I did not do anything much about the gravitino. And it turned out that the short thing I said was not quite right. So today I can do that more precisely, but let's do it at the end so that we don't waste the whole lecture with that, yeah? So indeed, yeah, yesterday I was saying that, so yeah, there was invariance of the action under transforming the gravitino in the following way, where this is some spinor, just with spinor index, no vector index. And so indeed, one can gauge fix this exactly in a way that removes this part. So the gauge choice would be gamma dot psi equals 0. And then one can see that there is again a residual gauge transformation. So, and it becomes exactly like in the case for the metric and for the gauge field. Namely, the residual gauge transformation is actually parameterized by spinors that satisfy the Dirac equation. Just like in the other case, it was scalar functions that satisfy the Clyde-Gordon equation. So there is a very close parallel between what happens for the spinors and what was happening for the bosonic degrees of freedom. But again, yesterday, I apologize, I wasn't precise about that. Should have prepared earlier. Okay, so let's move to the actual topic for today, which is how we dimensionally reduce 11-dimensional supergravity on a circle in order to obtain type 2A string theory. So I didn't point out this yesterday, but when I say string theory in these lectures, both yesterday and today, I always mean superstring theory. It did not occur to me, but you probably mostly talked about the bosonic string until now, but the more physical string is the superstring for various reasons. And that's the one that people consider when they try to obtain some low-energy effective actions that actually describe, say, the real world. So by string theory, I always mean superstring theory. And what I mean by reducing to type 2A string theory is actually going to be just to the low-energy effective action of type 2A, which is 10-dimensional 2A supergravity. And I believe that maybe next week or soon you'll see in the lectures that Freddy Cachazo is giving how the spectrum that we'll see appearing now after the dimensional reduction, how that spectrum appears when you quantize the superstring, the same spectrum at the lowest level, at the massless level. So you'll see next week, indeed, how this supergravity appears as the massless level of the quantized superstring. So today's topic is 2A. Well, okay, let's just call it string theory. Again, I always mean superstring. 2A string theory from dimensional reduction of 11-dimensional sugra. So for anyone who might not have been here yesterday, by sugra I always mean supergravity. This is a standard notation, standard shorthand for supergravity, just like SUSY is standard for supersymmetry. So the goal is now to reduce d equals 11 sugra on a circle, on an S1. So let me introduce some useful notation. So the indices M, N, like yesterday, are going to be 11-dimensional, but now it's convenient, and people often do that, to actually have the indices run up to 9 and then 11, because it's convenient to have 11 written explicitly. We'll need now to distinguish the 11th direction. So in particular, no 10 here. So the indices are going to run over 11 values, but they start from time, which is usual 0, and then go to 9 and then 11. This is going to be the circle direction that we want to reduce on. And other indices that I'll use will be small mu, which will be 10-dimensional. So these run from 0 to 9, and these are the 10 dimensions of superstring theory. Let's also call them 10-dimensional QA indices. And again, the circle is parameterized by x11. So this is the direction that we're going to be singling out and reducing. Yeah? Yeah, okay, at this point, you don't know yet, but when you quantize the superstring, you'll see that there are different options. And so choosing one option, you obtain QA. Choosing another, you obtain QB. And again, once you get to that, probably next week, it will be more clear how they differ by each other. But at this point, let me just say that, well, type 2B is not obtainable directly by reducing from M theory. There is a relation between 2A and 2B, but that's what is called T-duality. Some people may know about that. Others hopefully will learn maybe next week. But just from 10-dimensional point of view, so these are both theories that have n equals 2 supersymmetry, which means n equals 2 in 10 dimensions. So there are two spinors in 10 dimensions that are both parameters of SUSY transformations. And in 2A and 2B, the difference is that in one case, those spinors have the same chirality. In the other, they have opposite chiralities. I don't know whether I remember in which case what, but I think here probably they have opposite chiralities. Yeah. And in 2B, the same. So at this level, you can just distinguish them. Let's say that this is one SUSY parameter and another SUSY parameter. So in 2A, same opposite chiralities. Chiralities just mean, I think you know about Weyl spinors, right? So they are left and right Weyl spinors. This is the chirality, whether it's left or right-handed particle. Whereas in 2B, they have the same chirality. And what is the analog here of, so if you're in 4 dimensions and you talk about chirality, you look at the gamma 5 matrix, right? So in D equals 4, the chirality matrix is gamma 5. So left and right are distinguished, left and right-handed spinors are distinguished in this way. So you form 1 plus minus gamma 5 over 2, and you act on a Dirac spinor. So one combination gives you left, the other gives you right. These are the left and right-handed fermions in 4 dimensions. Now, let's call this left-right, and you understand that I think left is probably plus or right minus. I don't really remember, but this is really a convention. Now, in D equals 10, which is this chirality I'm talking about here, the analog is so-called gamma 11. So what is gamma 5? It's just the product of all 4 gammas. the gamma matrix is in 4 dimensions, gamma 0, gamma 1, gamma 2, gamma 3. So here, gamma 5 is gamma 11, which is the product of all 10-dimensional gammas, gamma 0 up to gamma 9. And then you use the same formula, but instead of this gamma 5, you put gamma 11, and this defines the two chiralities in 10 dimensions. So let me move this up. So at the level of supergravity, this is all I can say about the difference. But again, once you quantize the superstring, you are going to see more precisely what are the differences between 2A and 2B. And you'll see that also there is other option that is called heterotic string. And is also supersymmetric. So all supersymmetric string theories have critical dimension 10. They all live in 10 dimensions, but have differences in the way how they treat left and right movers on the world sheet. So, okay, I think today the lecture is going to go over time. So we want to reduce on a circle, which is the 11th dimension. So we want no dependence in the metric, in the components of the metric, on X11. So given that there is a one most general kind of ansatz for the metric, so let's write the 11-dimensional metric. Which is, just to remind notation, GMN, DXM, DXN. Now let's write it in a form that explicitly shows that X11 is an isometry, right? If nothing depends in the metric components on X11, it's an isometry, meaning that we can shift arbitrarily along that direction, and the metric will be invariant. So the most general ansatz is of this form. And now the small g is the 10-dimensional metric, the metric that will be for type 2A. And it depends only on 10-dimensional coordinates, not on X11. And we can have some function, again, of the 10-dimensional coordinates, multiplying the X11 plus, now we can have some one form, which again depends only on the 10 dimensions, d x mu squared. So this is the most general form of a metric with one isometry. And it's explicit that this metric does not depend on X11. That's what it means that it has isometry along this, because the only dependence is via dx11. And so when we shift by any constant, the differential kills that. So everything is invariant on the transformations shifts of X11. Now, if you're doing just supergravity and just say Coulson-Klein, which is the original dimensional reduction, just Coulson-Klein theory, this is probably the ansatz you're going to start with, and maybe even take some very trivial function here. But since we know that we are aiming at type 2A, we're going to slightly shift this. So if we don't do this shift here, eventually when we end up in 10 dimensions, we'll have to redefine some fields there. So now knowing about type 2A, we're going to slightly modify the ansatz so that we can end directly in string frame, in the action that one obtains from the beta function in superstring, in type 2A superstring, which again, hopefully you'll find out next week. So knowing about string frame 2A action, we modify the ansatz slightly. So again, we're doing this so that we don't have to redefine fields once we end up in 10 dimensions. And when we get there, I'll also remind you what it means to say string frame. There is also another frame called Einstein frame. And in Einstein frame, the gravitational action is the usual Einstein action. It's just the scalar curvature. The difference in string frame is that there is a e to minus 2 times the dilaton in front of the scalar curvature. But that's what occurs naturally just from the beta functions for the superstring. So that's where we want to end up. So the modified ansatz is going to be, so first we choose this function. With this in mind, we're going to choose it to be e to power 4 phi over 3, where phi is some scalar function. And also we're going to shift this metric. It's an arbitrary metric at this point, so we can shift it by any constant. I mean, we can rescale it by any constant. So we're going to rescale it in this way. We're putting an overall factor of e to minus 2 phi over 3 g mu nu dx mu dx nu plus e to 4 phi over 3 dx11 plus a mu dx mu square. So this will be the metric ansatz. Now, let me write again the fields. So now we identify G mu nu with 10D metric. Phi is a scalar. And when we get to type 2A, we're going to identify this scalar with the dilaton, the string dilaton. And the one form A mu that appears here, this 10D vector, it's also known as Kaluza-Klein vector in the literature on just Kaluza-Klein dimensional reduction. Let me write also that. KK vector. And in type 2A string theory, we're going to identify this with a, well, at this point, that doesn't mean much yet. But again, next week, you'll know what is a Ramon-Ramon versus Navier-Schwarz field. So this is going to be a Ramon-Ramon one form, the Ramon-Ramon one form of type 2A. And how is it a one form? Just in the usual way, namely a mu dx mu d is the one form that occurs in type 2A. So, yeah. Oh, you mean this and that? So, like I said, here I identified the function f with this. And here, what I do is I rescale this metric to this minus, so they're not the same. Or you can call this hat and then say that g hat is equal to this. Since it's arbitrary here, I can just introduce this factor. The whole thing still continues being arbitrary at this point. But like I said, it's useful to have this factor in the beginning so that we end up in exactly the right action in type 2A. Otherwise, we would have to rescale at the end, the final action. So this is just more convenient technically, but you could not know about that before you know what's going on. So now we can do that in hindsight, but originally it was done later on. Okay, so soon I'll also describe how the 3-form potential and its 4-form field strength reduce. But before that, it's useful to introduce something else. Well, okay, let me mention that. So now one can just substitute that whole ansatz into the 11-dimensional scalar curvature, and we'll get this is just a sketchy thing. At the end, I'll write the precise answer, but you're going to get some 10-dimensional scalar curvature plus some action with some numerical coefficients, some kinetic term for the scalar, and again some numerical coefficient and the kinetic term for, so F2 is the field strength of this one form, which is the related to the KK vector. So I'm going to write at the end the precise action that one obtains. So in this way, one can dimensionally reduce already the scalar curvature. But since the metric is not diagonal, and since in the full theory of supergravity we also have fermions and we want to couple them, it's more convenient, and for the fermions it's even necessary, not just a matter of convenience, to introduce a different notation rather than use the metric. The different notation is called Wilbein and Wilbein formalism. So let me introduce that. So this is just a way to go from a curved metric to a flat metric in which things are much simpler. So by definition, we have the following relation. The metric, the 11-dimensional metric, is going to be some new object, E, with lower index M and upper some other index that I'll describe in a moment. And then contract it with eta, where this is the flat metric. So this is the flat Minkowski metric in 11 dimensions. So these are curved indices, the usual curved indices we have. These are flat or tangent space indices. And these objects E are the Wilbeins. So they can be introduced in any dimension. Here we're applying this to 11, but this can be done in any dimension. Any curved metric can be written in this way. And again, this is necessary when one studies fermions, because we know that we actually describe the representations acting on the representations of the Lorentz group acting on the spinors in the tangent space. So we need to go to the flat indices in order to be able to couple fermions. So what else do I want to say about this? Well, since it's clear from here, I guess, but let me also mention that. So this transforms the curved index, transforms under general coordinate transformations. Whereas the flat index transforms under local Lorentz transformations. And I'm introducing the Wilbein now, although I only wrote the bosonic action last time, and so I'm not going to couple to fermions. But because even now it's going to be much more convenient to use the Wilbein rather than this non-diagonal metric when I'm going to reduce the 4-form of M theory. Any questions so far? Yeah?
When you go to the local running time,
Excuse me?
and you describe your states on the time space,
Mm-hmm.
can you relate those states on to the states of the curve space?
Yeah. So everything you relate. So I'll write that in a moment. But always every. No, the flat tangent space is tangent. So at every point of the curved manifold, there's a different tangent space. So there is a vibration of the local Lorentz tangent spaces along the whole curved manifold. But when you couple to fermions, you have to all the time transform to flat indices in order to write explicitly. And for every tensor, you transform the indices from flat to curved or curved to flat via multiplying with the Wilbein. As many indices as there are, you multiply each one with the Wilbein, and that's how you transform the indices. And I think it will become more clear shortly why it's actually a useful thing to introduce the Wilbein. Although I'll be a bit lazy and I'm not going to do the most technically involved part, which is actually reducing the 11-dimensional scalar curvature. That's much more involved technically than anything I'll do now. And then it's really useful to use flat space rather than the whole curved magic. But I'll just do a simple part of the reduction, which is related to the 3 form and its field strength, that is a 4 form. And then I'll state the final answer for everything. So, okay, let's introduce the Wilbein for the metric that I wrote on the other board. And so, in the present case, EAM dxm looks in the following way: E2 minus phi over 3 E A mu, where now A is a 10-dimensional flat index. And mu was the 10-dimensional curved index. So that's a 10-dimensional Wilbein. Dx mu plus E to 2 phi over 3. Is this too small? Okay. Dx11 plus A mu dx mu. And you can easily convince yourselves that if you multiply two expressions like that and contract them with the flat metric, say you take EAM dx m times EBN dxn, and you contract with eta AB, you can easily multiply this and see that indeed you get exactly GMN dx m dxn. Exactly the metric G that we have there with the ansatz. Oh, I think you're right. Yeah, that's a type. Sorry. Okay, very good. So yeah, so the Wilbein is a matrix. It has two indices. No, this is 10 and this is 11, right? So yeah, okay. So if you write as a matrix, no, it's nothing strange. This index M runs over mu n11. Here you mean? This is just a number, right? Here, yeah. No, but this is a superposition of forms, right? This is a sum. Again, this index goes, when the index runs over mu, you have this term. When the index runs over 11, you get that term. No, but that's also the same thing. Okay, let me write as a matrix. The index A also has values. The capital index A goes over small a and 11. Just like the capital index M goes over mu and 11. Right? Because the flat space has the same dimension as the curved space. It's just the flat tangent space at a particular point of the curved manifold. If the manifold is d-dimensional, the tangent space is d-dimensional as well. So for the curved 11-dimensional manifold, the tangent space is 11-dimensional as well. So this is a correct statement. On both sides, there is equality of matrices. If you remove the d's, I'm going to write now as a matrix. I don't know, maybe that's more illuminating. So the matrix components are e2 minus phi over 3, e a mu, 0, e to 2 phi over 3, a mu, e to 2 phi over 3. And so this clearly is the a mu component. This is the mu 11. This is the a 11. And this is the 11 component. Right? So now you're happy with this? Okay. So this equation? For capital A equals 11. So these are the two components, right? So this is the, so they say there is no A11 component, and the 11 is this one. It's this the 11 component, right? Because I don't know why this is confusing. Think about, so this you can call E, so this is E mu A. This would be E mu 11, and this you call the vector A mu. Okay, so I don't know whether it's more illuminating or not, but this is what I mean. This is the matrix.
So you mean that the second A part, you have a delta A11, right? No. There in the second part, it's only that was when A is 11. Yeah.
No, here A is any of the 10-dimensional, and this is the 11th value of A.
Okay, but then if you want to write it, so you should have delta A11, capital A11.
And the same in the first one.
Use the notation. Delta A11.
Okay, take two matrices like that, multiply them, and you'll see that you get exactly that matrix, if you're happier with that notation. So, well, I don't know whether I wrote that matrix somewhere, but you can just read it off from there, and you can convince yourselves that this matrix multiplied with another one with indices Pn gives you exactly this matrix. So, and let me also write the inverse, because that will be useful too. Here this. I don't know, maybe I should have written this in two parts for the different values so it's less confusing. But I think that this is the correct statement that you cannot disagree with. So the inverse matrix is, well, e to phi over 3 e a mu 0 minus c to phi over 3 a e to minus 2 phi over 3. So, okay, let's just talk about matrices and never look at this. So you can convince yourselves here that if you multiply, say, well, if you do matrix multiplication, this is going to be delta AB, and similarly for the other indices. So you can check for yourself. So this is indeed the inverse metric. the inverse Wilbein. And actually, this is the one that we're going to use now. Maybe to avoid any kind of confusion, let me just write the various components. So A mu is e to phi over 3 e A mu. A11 is minus e to phi over 3 A. A11 mu is 0, and 11 is e to minus 2 phi over 3. So these are the components of this matrix. That is the inverse Wilbein. Okay, I'll go here. Any more questions about that? Yeah?
A index, little a.
Little a is in 10 dimensions, the flat index.
Big A index, little a.
That should be mu.
No. You're asking about this, right?
Yes, what is that?
So this is the one form, right, that came from A mu, d mu, dx mu. Now, if we write it as a flat index, we can write this as E mu A, A. So multiply by the Wilbein or the other way. A with, this is 10-dimensional flat index. So this is going to be equal to A mu multiplied with the Wilbein mu A. So just look at the component there, mu A, which is e to phi over 3 times e A mu. And this gives you how you go from flat to curvy indices. So now, I'm not going to let you go soon. Now let's reduce the 4 form, that is the field strength of the 3 form. There's not going to be time to talk about the Gravitino, so if anybody is interested, you can look for me or you send me an email. You can find my email on the string group webpage. So, okay, so the 3 form in 11 dimensions, there are clearly 2 choices. We can take one of the indices to be along 11, and then both the others have to be along the 10-dimensional mu nu indices, or all 3 can be along the 10-dimensional indices. No more than one can be 11 because it's antisymmetric. So there are 2 choices. We can have either mu nu rho or mu nu 11. And this is actually the B field in string theory. You're going to see that, or maybe you've seen already. I don't know how far you've gotten. This is a universal field that appears in all sectors, in type 2A, type 2B, in heterotic. So this is the B field that appears when you quantize string theory. And in the context of type 2A, this is going to be a Ramon-Ramon 3-form potential. So let's see now what happens with the 4 form, that is the field strength of this. So now it will be useful to use those Wilbeins that send us to flat indices. So let's look at in 11 dimensions, the 4 form. If we write it in flat indices, it just means that we have to transform each index with the Wilbein. So again, going to flat indices is useful because in flat indices, everything splits directly into 10 and 11 dimensions, whereas with the curved indices, because the metric is not diagonal, there are always more involved things. So this is the easiest way to do the reduction. So again, there are two options. Let's first look at the simpler one, technically, which is to take 3 to be along the 10-dimensional flat indices, and the fourth index to be 11. And the other option is all 4 to be along the 10-dimensional flat indices. So here, writing those Vilbines, we have a mu with indexes b nu, c rho, and 11, 11, mu nu rho 11. And this is a unique contribution here because we see one index has to be 11, and we see there from the table that when the lower index is 11, the upper index can be only 11. The other components are 0. So, and the moment this is fixed, then all the other indices have to be along the 10 direction. So there is only one kind of contribution for this decomposition. And we see, substituting the Vilbines from that corner, we see that this gives, so from the first 3 Vilbines, we have e to pi over 3 cubed, and then EA mu. I'm doing this slightly more in detail than necessary, maybe, because the next case with all 4 indices along 10 dimensions will be a bit more involved, and I'll have to rush through it. So I'll write this now for more clarity. B mu C rho, and then e to minus 2 phi 3. So these all came from the Vilbines. Now this I'm going to denote h mu nu rho, and this is the field strength of B. So as a 3 form, H is D of B2. B2 is this 2 form. So here we get H mu nu rho. So now with those Vilbines, all of those indices become flat, and we can simplify the exponentials, and we just get e to phi over 3 h a b c. Now the second case is a little more involved. So the second case is when all 4 indices are along the flat 10-dimensional directions. And now we're going to have 2 options. So one option, again, this can be seen just by looking at the form of the Vilbines. One option is to have this, E A mu, E B nu, E C rho, E D sigma, with F mu nu rho sigma. And then there is another option, which is E A 11. And now that this index is fixed to be 11, all the others have to be along the 10 dimensions. So B nu, C rho, d sigma f11 nu rho sigma. And I left a little space here because clearly there are 4 choices for where to put the index 11. So we have 4 terms like that. And also we have to keep in mind that this is anti-symmetrized because this is the original form is anti-symmetrized. So here I write it explicitly because it seems like there's a difference between the indices. Here it's already automatically taken care of by this anti-symmetry here. So that's why in this term I wrote explicitly the anti-symmetrization. So now we can substitute the Wilbines from that corner, the inverse Wilbines, and we get, so here I'm not going to write all intermediate steps. This is just 4 phi over 3 times f a b c d plus 4 phi over 3 a oh, okay, I forgot. There is one more phi. Well, I'll write it in the end. 11 BCD. Sorry, this should have been already taken into account, but let's keep it. And this is H BCD. So finally, we have e to 4 phi over 3, which is common for both terms, f a b c d plus 4 a with index a h b c d. So we can notice, okay, let's keep the same kind of bracket. This combination is often denoted f tilde. It's a 4 form, and writing it as a form, it looks the following way. So as a 4 form, this is f4 plus 4 a1 wedge h3. And this is exactly the form that is going to appear in the action. And again, this was the one form coming from the Kaluza-Klein vector. So, okay, before I turn to the action, let me also say what do we do with x11. So now nothing depends on x11. The metric components are not functions of it, and all the other components are not. So how do we get rid of that? So we integrate over x11. And that means that, so in the 11-dimensional action, we have a term, well, the beginning of the action looks like, let me write more precisely, there is the gravitational coupling in 11 dimensions, kappa squared, 1 over 2 times kappa 11 squared, times integral d11x plus the rest of the action. So now, by integrating over x11, which is a circle, we're going to have the same prefactor, but now from integral over x11, we're going to have 2 pi r, which is just coming from integral over s1, which is parametrized by x11, and then integral over the remaining 10 dimensions, and the action that we obtained here by reducing all the various terms. So what that means is that we redefine the gravitational coupling constant. So we have that in 10 dimensions. So right, this whole combination has to be the 10-dimensional 1 over 2 kappa 10 squared. So then that means that kappa 10 squared is equal to kappa 11 squared divided by q pi r. And a standard notation is, well, kappa in any dimension, actually 11 or 10 doesn't matter. It's just, what was the prefactor? Something like a 16 pi, the usual Newton constant, gravitational constant. So, but somehow people more often use kappa than Newton constant g. Newton's constant. So that means also the Newton's constant transforms in the same way. The 10-dimensional one is equal to the 11-dimensional divided by 2 pi r, where r is the radius of the circle. And from the perspective of type 2a, we're going to see that actually the radius of the circle is related to the strength of the string coupling. Or maybe you are going to see that next week. So let me just write, I don't know where is suitable. Okay, maybe on this side. Let me just write the action. We're almost done. So any questions so far? And similarly, you can reduce on many other directions. Like I was saying, you can get up down to 4 just by viewing each direction in between as a circle. And so you're going to end up with n equals 8 supersymmetry. However, if you want to build models of particle physics, you want less supersymmetry. And in those cases, people reduce on some other manifolds that have some special property. They're called special holonomy manifolds. And the famous example for string theory is Calabi-Yau manifolds. But for 11-dimensional supergravity, the analog of that is so-called G2 manifolds. And when you compactify on them, you actually get just n equals 1 in 4 dimensions, meaning only 4 supercharges in 4 dimensions. And those are starting points for actually model building for particle physics and things like that. But we are not going to cover this here. So let me just write the action, and maybe I'll let you go soon. So combining all those ingredients of substituting the metric ansatz, reducing the 4-form field strand, and integrating X11, we obtain finally the 10-dimensional 2A action. So again, at this point, you don't know that it's type 2A, but next week you'll recognize the same fields that we found here from the dimensional reduction. You'll recognize them as appearing from quantizing the supersymmetric string. And you'll recognize them by counting the physical polarizations, like I was doing yesterday, not from effective space-time perspective. The effective space-time perspective comes when you look at the beta function, and then you can write some effective field equations that are low-energy approximation. But you're going to recover the actual physical states from quantizing the string. So the 2A action has 3 terms. Let me write them separately to underline their meaning. NS stands for Navier-Schwarz. This is Ramon. And a Chern-Simons term. And this action is universal for all string theories, not just for type 2A. Whereas this depends on the type. And this is because in different, well, including with the Chern-Simons term, it's because in the different types of strings, there are different types of Ramon-Ramon fields. So the universal part is 1 over 2 kappa 10 square d 10 x minus, well, square root of minus determinant of the metric e to minus q phi r plus 4 d mu phi minus 1/2 H3 squared. And again, this is the scalar curvature, but now in 10 dimensions, and this is the duotone. And this factor here means that this is string frame. This is what I was mentioning before. String frame is what you obtain directly from the beta function of the quantized string, whereas Einstein frame would mean rescaling the metric by an appropriate e to some power of the duotone, so that this factor disappears and you just have directly the scalar curvature. That's the usual Einstein action in 10 dimensions, yeah? So yeah, so that's the leading effective action. Of course, at next order, there will be other corrections that are higher derivative terms and such. So, well, this is contracted. Oh, sorry, these are mu indices, right? These are 10-dimensional. This is just the kinetic term for the duotone. And H3 squared means, well, the usual contraction, let's see, probably there is some factorial, but something like that, M1, M3, N1, N3, contracted with the metric. Yeah, that's the, sorry, this is already 10-dimensional, so this should be mu. And nu. And these are all contracted, mu1, mu1, mu3, mu3. And probably there is 1/3 factorial. So, like I said, those fields are universal for all strings, the metric, the duotone, and the B field. This is the field strength of the B field. And so their action is also universal. Now, the contributions that depend on the type, the Ramon piece that we obtain now, which is the one for type 2a, is the following: minus 1/4 kappa squared. Did I write explicitly? Okay, 10. So this is the 10-dimensional gravitational coupling. D10 x, again, minus determinant of the metric. And now this is just the kinetic term for the two Ramon fields that we have here. And this is F tilde 4. So this is the combination that occurred here that contains both the field strength of the tree form and this term that couples the field strength of the B field with the field strength, with the potential from the Kaluza-Klein vector. So this is that combination F tilde. And F2 is again just, so F2 is just dA, the Kaluza-Klein. And F tilde is the expression from there. And the Chern-Simons term, if I write here, do people see? Okay, let me just write this here, and I'll raise the board just in case. Okay, I guess I should finish soon. So the Chern-Simons term looks the following way. It's the same prefactor. And then we have B2 wedge F4 wedge F4. Okay, so this is the bosonic action for type 2a string theory. Like I said, hopefully you'll recognize next week how those things occur from the string perspective. And I should have said also something about the fermions, but there is not much time. So let me just say in words. So we had only the vector spinor in 11 dimensions. And when we fix the vector index to be along the 10 dimensions, that gives us two gravitinous in 10 dimensions, which are the two gravitinous in type 2a that have opposite chiralities. Whereas when we fix the vector index to be 11, that gives two spinors in 10 dimensions that are called duotinous. They also have opposite chiralities. And this field content of gravitinous and duotinous also exactly matches the field content of 2a string theory at the massless level. So here we saw how the bosonic fields work out. For the fermionic fields, things also work out. So you'll have to trust me on that. But it's a fact. And okay, are there any questions? I think probably that's all I can say today. Yeah? Yeah, yeah, the 11-dimensional supergravity Bosonic action. And when you substitute all those reductions, you end up with these actions.